and you end up getting, you vaporize either the warm water itself or a working fluid, and then you run that vapor is pressurized by the evaporation process, and it turns a turbine, and you get electricity out of it. And it's a very plentiful resource. The oceans are very big, and there's I think the number is something like 13 terawatts of energy continuously is available from this resource without significantly changing the temperature structure of the ocean. Global warming is doing a much bigger job of changing the temperature structure of the ocean than anything we could have thought of doing with OTEC back in the days when we were trying to figure out how to do this back in the 70s and 80s.
Geez, now here at the NELHA, and tell me what that stands for.
The Natural Energy Laboratory of Hawaii Authority.
Well, that cold water has a lot of other uses, right? Tell us about that.
That's what it turns out that we can get many, we used to call them byproducts of this ocean thermal energy conversion process. And there are lots of different projects going on here. Right now we're at the place where they're doing the research on ocean thermal energy conversion. But there are lots of projects growing various things which will grow in the cold water but won't grow in surface seawater here in Hawaii. So that's partly a temperature issue, and another big issue is that the cold water is very rich in nutrients. The nutrients are in the algae that grow in the surface layer, and the algae die and then they sink down into the deep water. And so the nutrients have been taken out of the surface water, and so the surface water in the tropics in general, and here in particular, the surface water is depleted in nutrients. So if you bring up the deep water and mix it with some surface water, you can get any temperature you want between very warm, between the top temperature, which is on the order of 78 degrees, 76 I guess is the year-round average Fahrenheit, and you can then get any temperature between that and the deep water, which Steve mentioned that the pipe is 2,000 feet deep. That was the original pipe, which is right out here. We've put in a new pipe that goes to 3,000 feet deep, and that's the optimal depth for doing energy conversion. That's the number, that's sort of the magic number. It's at the bottom of the thermocline. When you get down below that, the temperature doesn't change much. It stays cold all the way down. The temperature at that depth is about 4 degrees Celsius, and seawater doesn't get any colder than what's that, 41 degrees Fahrenheit.
So why don't we use that now to create energy? Is it too expensive compared to other things, yet still something we could avail ourselves of?
It is still a potential. It is, I've been working on this now for 40 years, and during that time we've gone through various stages of competitiveness with alternatives. And the alternatives traditionally were all oil. Now we're getting to the alternatives of photovoltaic. And photovoltaic is now getting down to being more than competitive with oil in a lot of situations. So that's the preferred technology. We were competitive with oil at various stages in its development. But the big problem with this technology, the reason we're not using it more, is that it's inherently large scale. To pump up the deep water, you need a large system to get the water up to the surface. There are also proposals, I should say, for doing it down at the bottom of the ocean, basically pumping the surface water down. But those are even technologically more challenging.
It's
Generally.
amazing what goes on in the Big Island. I mean, I was always struck by, at a later time in your career, you were tapped by a Silicon Valley company to come up with, was it called Wave Glider, which was basically a surfboard with sensors on it, because a very wealthy individual who was smart enough to hire you as the chief scientific officer couldn't hear the whales in front of his oceanfront house, right? Because the fishermen kept hitting the cables, so he needed a floating hydrophone to hear them, and that idea became one of the things they began to sell to the government for 300 grand, and places like Scripps, I don't know if they've copied it, they're probably a little jealous, and the thing can be operated from a phone all the way to Japan, right? You can float this sensor device.
The critical thing about the wave glider is that it's powered by the waves, and so you don't. The waves exist everywhere in the ocean. All the other sources of energy which you might use for powering through the water are variable. Wind, photovoltaic. Those are the two main ones, and now that our battery storage systems are getting better, you can actually store, you can now do better with photovoltaic, but you need to have a very large surface area to collect enough electricity to run, to get any propulsion and to run experiments.
Right.
So the wave glider uses wave power for most of its motive power. The newer model, when I worked on it, we didn't have any other source of energy on board other than waves. Now they have a photovoltaic powered motor which enables it to maintain a constant speed even in areas where the currents are opposing it and where the waves aren't as pronounced.
Very cool, very cool. So what else is here at Nelha? I mean, you've got like tasty abalone, you know,
Yes, we've
spirulina got, for all the hippies in the audience, you know. This is where it's made with big paddles, cyanotech, and bioastin, right? Wasn't that supposed to turn the farm-raised salmon pink, or
yes,
am I
the
wrong?
initial idea was that the astaxanthin that comes out of the algae that they're growing was going to be used as an additive to salmon feed for salmon farms. It turns out that some of the synthetic ones, substitutes for astaxanthin, which were initially declared as non-organic and therefore were not appropriate,
right.
Have now somehow, because they're so much cheaper, they've become appropriate.
So we're not, I mean, my salmon from the farm is not being, it's one thing to have it turned pink by algae from deep water, right? But now, but now it's artificial.
Yes,
huh.
And I believe it's Hoffman LaRoche is the parent company that is part of the whole process that somehow got astaxanthin improved for salmon feed. I mean, got the artificial substitute for astaxanthin.
Well, it's a wild world out here in Hawaii, where soon it'll all be running off of alternative energy, as we discovered yesterday at Tetris Blue Planet. But what else is here? I mean, and the reason why things like can be grown here is you can regulate the temperature, and some of them require very cold water, like lobsters, right? So they can use the cold water that's being pumped up from 2,000 to 3,000 feet.
Well, and the neat thing is we can provide any temperature of flowing seawater between about 6 degrees Celsius and the typical water temperature here, which is 28 degrees Celsius. So that's between 40 somewhere around 41 degrees to 78 degrees year-round. You can just turn a valve and you can get any temperature that you want. And so there's a lot of things that can be done to speed up the breeding cycle and the life cycle of all kinds of organisms by experimenting. We don't know because nature doesn't do it that way. But we use the cold water to chill the soil under some plants. That turns out not to be a really commercially viable thing yet, because you have to have a place where you have soil and you have a crop to grow. We don't have soil down here, so we brought some in, and we grew strawberries. We can grow strawberries by just running cold water pipes running cold water through pipes that are right under the roots of the strawberries.
Wow.
You can make you can get 10 times the sugar content of strawberries that are grown up in Waimea, which sell very well locally here. That's at 3,000 feet. It's cool enough there so the strawberries will grow. Here,
Wild strawberries, to quote Bergman, little joke there, film joke.
yes.
Oh, and what else? Strawberries, abalone, lobsters, spirulina.
Yeah, all kinds of crustaceans in addition to the lobsters, and lots of shellfish of all different kinds, oysters, abalone. You said there are lots of different things. We have companies from all over the world who are doing experiments with all of these things.
And one of the new ones is Symbrosia, which will solve or attempts to solve the cow fart problem. They just got a 7 million Series A, and the idea is, I believe it's a red algae, which is like astrozantha. No,
I can't remember the name.
It starts with an A. I've
Yes.
lost it here too.
Anyway, they found a variety of the red algae, which is apparently the most efficient at reducing methane emissions from cows, and they actually were the first ones to actually do a field study on a farm, I think in New York State, and demonstrated a dramatic reduction in methane emissions, which is pretty critical because methane is 4 or 5 times as efficient a heat absorber as CO2. So it's worse than CO2, and
Much worse.
We put a lot of effort into trying to reduce our CO2 emissions. The main sources of methane emissions, there's a lot of it stored in the crust of the earth, and one of the big fears that is that as warming goes on, the crust will warm up, and all of the methane that's stored there in the soil under the Arctic and in the deep ocean also, that will come into the atmosphere and dramatically accelerate global warming.
Well, that's one thing, but this ought to take care of those pesky cows, you know.
Yes, right.
And it's asparagopsis
Yes.
is the hard to say word. You know, Tom, this has been a great interview. Sorry to make you look in the sun like this, and it's hot down here on the Kona coast, but we have to run for the airport back to LA. Thanks.
Thank you.